Okay, so you guys have given us quite a task today, really. How do we keep our cars safe from getting, well, hacked, basically, as they become more and more like rolling computers, right? We've got this really cool pile of research here focusing on this thing called the CAN bus. I guess you could call it the communication network of your car. And it seems like there's this whole new system that uses AI to try and catch those attacks quickly and hopefully, before anything bad happens. So, our mission, if you will, is to break this down and figure out if this could be the answer, right?
Yeah, absolutely. And I think the core of all of this is something called the Controller Area Network, or CAN bus. It's kind of like the nervous system of your car. It's what lets all the different parts talk to each other, like all the electronic control units, those ECUs. Everything from your engine, your brakes, airbags, even the radio. I mean, it all uses the CAN bus. So you can see how, if someone messes with that, well, we can really mess up the whole car.
Okay, so it's the backbone, right? Like the a central nervous system. But I'm guessing this backbone might have some weak spots, right? Like it wasn't really designed with all these online threats in mind, was it?
Yeah, that's a really good point. I mean, the CAN bus protocol is actually pretty old. It goes back to the 80s. And, well, it doesn't have these basic security things built in, like encryption, for example, or authentication. You know what I mean? So if someone figures out how to tap into this network, they could potentially, well, listen in on everything that's going on, or even send their own messages, which is obviously not good.
Yeah, that opens up a whole can of worms, right? Speaking of which, I think the research talks about three main types of attacks. Can you walk us through those and what they might actually look like, if they happened?
Sure. So the first one, they call it message injection. Think of it like an attacker basically spamming the car system with fake messages. They just flood the CAN bus with these bogus messages. And if they send enough, they can drown out all the real ones. That could, disrupt how the car works or even potentially take over certain functions. And, if they target like the engine or safety systems, that's where it gets really dangerous.
Yeah, it's like a digital denial of service attack, right? Or maybe like just throwing a wrench into the gears. I think they call that a fuzzy attack, right? Just random noise to mess things up. What about the second type?
That's message suspension. This is where an attacker might, for example, take control of one of those little computers, an ECU, that, let's say, reports the car's speed and just stop it from sending those messages, which again can be really bad because other parts of the car might need that information to work properly, like anti-lock brakes or traction control.
So they can essentially disable safety systems. That's scary. And the third type,
The third one is message falsification. This is where they mess with the content of real messages, like they could replay old messages or make up completely fake data. And the tricky thing here is if you're only looking at the timing, when messages are sent, it might look perfectly normal.
so they could make the car think the driver isn't braking, even AAR, or that the steering wheel is turned the wrong way. That's not good. Now, the research talks about how the current ways we try to protect cars have some limitations. What are some of those?
Right, so many of the systems we have now, they're only good at catching like one or two of those attack types. They might be great at spotting a sudden flood of messages, but miss something more subtle. And a lot of them need a ton of data to learn what normal looks like before they can spot anything suspicious.
Which means there might be a delay, right, before it actually figures out there's a problem. Not ideal when we're talking about safety. Which brings us to this new system, the Federated Graph Neural Network, right? That sounds pretty high tech.
Yeah. So the main idea is using a graph neural network, a GNN, and they claim it can detect all three of those attack types at the same time and really fast, within like 3 milliseconds. That's super fast, practically instant. The federated part we'll get to later. That's about letting cars learn from each other safely. But yeah, the GNN is the key here, how it looks at the data from the CAN bus.
Okay, 3 milliseconds. That's faster than you can blink. So how does it do that? Let's go back to those attack types first. Can we get some really clear examples from the research so we can really picture how these attacks would work?
Sure. So for message injection, let's say an attacker keeps sending messages with a really low CAN ID. Think of the CAN bus like a radio channel. Messages with lower IDs get to talk first. That's how important messages get through. So by flooding the channel with these fake low ID messages, they can basically block the real ones. The paper also talks about those fuzzy attacks where they just send random junk. Even if those IDs aren't being used, they can still mess things up.
It's like someone jamming the radio, right? Or just shouting gibberish so no one else can get a word in.
Exactly. Now, with message suspension, imagine the part of the car that reports how fast the wheels are turning. If an attacker stops it from sending any messages, well, things like anti-lock brakes or traction control, they might not work right because they need that information to function.
So they could make the car behave unpredictably in a dangerous situation. That's unsettling. And what about message falsification? What's a really concrete example of that?
Think about your cruise control. It works by receiving messages about the speed you want to maintain. An attacker could mess with those messages, making the car speed up or slow down without you doing anything. Or, back to the brakes, they could make the car think the brakes are off even when you're pressing the pedal. The key point is the timing might look normal, so it's really hard to catch unless you're actually looking at the content of those messages.
Wow. Okay, so these attacks target really different parts of how the car talks to itself, right? So yeah, catching all three at once, that's a challenge. The research mentions that some older methods, like having separate detectors for each channel or combining multiple detectors, can get really complicated and slow. Why is that?
Well, think about how many different communication channels, those CAN IDs, are in a car. Having a separate system for each one, that's a lot of processing power. And if you have multiple detectors trying to put all their adults together, that takes time. And, when you need to spot a threat in milliseconds, any delay is a problem.
Right. Okay, so we need something that can see the whole picture quickly. That's where the GNN comes in, right? So how does this thing use these graph neural networks to analyze all that complex communication?
So what it does is it takes all that CAN bus data, that constant stream of information, and every few milliseconds, it basically takes a snapshot, like 100 to 200 messages, something like that. And from that, it creates what they call a CAN message graph.
A graph, with circles and lines. How do you turn card data into a graph?
Yeah, exactly. So the circles, they're called nodes, and each node represents a different CAN ID that was active in that little snapshot of time. So if you had messages with like IDs 0 by 100, 0 by 254, 0 by 312, those would be three nodes. And each node has these attributes that tell you about the data in those messages. Like the paper mentions this IT method they use to look for any weird changes within the data, like bits being flipped, which could mean someone's tampering with it. Oh, and if a completely new ID pops up, that could be a sign of a fuzzy attack.
Got it. So the nodes are like, here's who was talking and here's what they were saying, and you're checking if anything in that saying looks suspicious. What about the lines connecting the circles? What are those?
Those are the edges. They show the order in which those messages appeared. So if message 0 by 100 came right before 0 by 254, you have an edge going from the 0 by 100 node to the 0 by 254 node. And those edges have weights, which basically say how often that particular sequence happened.
Right, because like the research said, usually the order of messages is pretty consistent. So a change in that order or how often it happens could mean something's wrong.
Exactly. By looking at both the content of the messages, that's the nodes, and the order and frequency, that's the edges and their weights, these graphs give a much more complete picture.
So it's looking for weird patterns in both what's being said and how it's being said. Makes sense. Okay, now, the research mentions a two-stage classifier. Why two stages?
So the two stages are there to solve a big problem in cybersecurity. We don't usually have a lot of examples of real attacks to work with. We have lots of normal data, but not much attack data.
Right, it's hard to teach a system to recognize something it's never seen before.
Exactly. So the first stage is all about anomaly detection. It's trained mostly on normal data. And instead of classifying attack types, it uses this special thing called a one-class classification layer. It's based on something called Support Vector Data Description, or SVDD. Basically, it learns what normal looks like and flags anything that's too different.
So stage one is saying, hey, this looks weird. What happens then?
If it finds something weird, that data goes to stage 2, which is about attack classification. This stage is trained to recognize specific attack types, like those denial of service, fuzzy, suspension, replay, and spoofing attacks we talked about. But here's the really cool part. They added this thing called an open max layer.
Open max layer. Okay, what's that?
This open max layer is there to deal with completely new types of attacks, the ones we haven't seen before. Instead of trying to force it into one of the known categories, it can say, hey, this doesn't match anything I know. This could be something new.
So it's not just looking for the bad guys it already knows, it's learning to spot new ones. That's awesome.
It is. It gives the system a way to adapt, which is really important. Now, another key part of this research is the federated learning. You remember how we talked about how the CAN bus data can change depending on how the car is being driven?
Yeah, like driving conditions, even the driver's style can make a difference, right?
Exactly. Think about it. A car sitting at a red light will have different messages than a car speeding down the highway. Even the tire pressure sensors might only send messages at certain speeds. And a driver who slams on the brakes a lot will create different patterns than someone who drives smoothly.
So if a security system only learns from one car, it might not work well for other cars or in different situations. It might mistake normal variations for attacks or miss real attacks because they look like a different driving style.
Exactly. That's where federated learning comes in. It lets lots of cars work together to build a better model. But, and this is important, none of the actual data leaves the individual cars. Each car trains its own little model, and then they only share the learned patterns, not the data itself. Then a central server combines those patterns to create one big super certain model.
So it's like crowdsourcing security, right? Everyone helps out without giving up their privacy. The research mentioned these FedEv and FedProps algorithms. What are those?
Those are ways to combine the models in federated learning. FedAB is like taking the average of all the little models. FedTrox is a bit fancier. It adds a little constraint to make sure those little models don't stray too far from the main one.
That makes sense. Okay, so how well does this whole system actually work? What did the experiments show?
The results are really promising. It could detect all three attack types and fast within those 3 milliseconds. And it performed as well as, or even better than, existing methods, especially for those message injection attacks. The OpenMax layer worked too. It could flag new attack types. And as expected, the federated learning helped a lot because it learned from so many different driving situations.
That real-time detection is key. And the paper also mentioned the system can handle different lengths of those data snapshots and that the first stage doesn't use much memory. Those are good practical things, right?
Yeah, definitely. The flexibility with the snapshot lengths means it can adapt to different situations. And low memory usage is important, especially in cars where you don't have unlimited resources. They do point out some challenges, though, like distinguishing between really subtle attacks like a replay versus a spoofing attack where only a tiny bit of data is changed. That's something they're still working on.
Right, making it sensitive enough without getting too many false alarms. That's always a balancing act. So what's next for this research?
They want to use those unknown anomalies they're collecting to learn more about new attacks. And they need to adapt it for different car models because CAN bus communication can vary. And of course, they need to keep improving the security and privacy of the federated learning itself to make sure no one can mess with the learning process.
So it sounds like this research is a really big step forward in keeping our cars safe. It's not just about reacting anymore, it's about learning and adapting.
Yeah, it's about using AI and collaboration to stay ahead of the bad guys while also respecting people's privacy.
It makes you wonder what the future holds, right? As cars become even more connected, self-driving, how will these systems evolve? And what role will things like federated learning play in keeping us safe? That's definitely something to think about. For all of you listening, if you want to learn more, check out the research. It's really fascinating stuff. Thanks for joining us on the deep dive.